Hey guys, this is proof 11.2, and once again the disclaimer is that this is not sufficient for you all to write only this on your final exam if 11.2 does end up being one of the proofs asked for you to present. But you'll need to sort of narrate your steps through the proof. I've put the important steps in green, really key elements in my opinion in blue, and so here we go. Let x be a manifold known by a real valued C1 function, capital F, which is our constraint function, where capital F goes from an open subset of U of Rn to R, and df, the Jacobian of the constraint function, is nowhere 0. Let little f, which is going to be our optimizing function, go from U to R via C1 function. So the fact that I called big F the constraint function and little f the optimizing function should sort of ground you a bit in Lagrange multiplier lingo. So we prove that A, an element of X, is a critical point of the optimizing function restricted to the manifold if and only if there exists a Lagrange multiplier lambda such that D little f, so the Jacobian of the optimizing function, is equal to lambda times d big F, which is the Jacobian of the constraint function. So there are a few steps before we even really get into how we're going to prove this, and it's important that you write them out. We have that the tangent space to the manifold at point A is a subset of the kernel of the Jacobian of the optimizing function. This is a result from 11.1. We also have that the tangent space to the manifold at point A is equal to the kernel of the Jacobian of the locus function, or the Jacobian of the constraint function at point A, and that is from 10.2. And we can take both of these as given for this proof. So just plugging in this identity right here into this statement, we have that the kernel of the Jacobian of the constraint function at A is a subset of the kernel of the Jacobian of the optimizing function at A. And that is really important for this proof. Similarly, we're only going to do the case where we have one constraint. So that means that the Jacobian of our constraint function is just going to be one row with many, many columns, n columns. And similarly, the Jacobian of our optimizing function is going to be one row with n columns. We're going to call the Jacobian of our constraint function alpha, and the Jacobian of our optimizing function beta. So just translating that into our new shorthand, we have the kernel of alpha is a subset of the kernel of beta. So we begin this proof. The if direction is pretty nice and easy, so let's do that first. That means that we are assuming that there exists some lambda such that beta equals lambda alpha. And we choose a vector v that is an element of the kernel of alpha. So it's an element of the kernel of the Jacobian of the constraint function. So if this vector v is a critical point, multiplying it by the Jacobian of the optimizing function should give us a 0. And we've chosen that v is in the kernel of alpha, so the Jacobian of the optimizing function in A times v is going to, in our shorthand, be equal to beta v, which subbing in beta equals lambda alpha, we have lambda alpha v, and that gives us 0 because v is in the kernel of alpha. So sure enough, we have that the Jacobian of the optimizing function acting on v gives us 0, and we have a critical point. This works for any vector in the tangent space of capital F or the manifold X. And that's our if side of the proof. It's a little bit trickier here to prove that the fact that this Lagrange multiplier exists is necessary and sufficient. So the way that we do the second half, which is a little bit more complicated, is a proof by contradiction. So that means the first step is we're going to assume that there is no Lagrange multiplier. So beta does not equal lambda alpha for any value of lambda. And we're going to construct some matrix A, which has alpha on top and beta on the bottom, So it has the Jacobian of the constraint function on top and the Jacobian of the optimizing function on the bottom. And since we know that alpha is not a multiple of beta in any way, we know that A is onto. It has two linearly independent rows, two linearly independent columns, and so we know, since it's onto, a solution exists for this equation. A acting on some vector v can give rise to 0, 1. And so since we've chosen this solution, this is another nice axiom of choice. We've chosen this solution intentionally to give rise to this situation. Alpha acting on v is going to give us 0. Beta acting on v gives us 1. That's just by looking at what A is comprised of. So what does that mean? Well, v is in the kernel of alpha here, so v is in the kernel of the Jacobian of the constraint function. But here, beta acting on v gives us 1 and not 0. So v is not in the kernel of the Jacobian of the optimizing function. But up here, we used our previous knowledge to show that the kernel of the Jacobian of the constraint function was a subset of the kernel of the Jacobian of the optimizing function at a point that is a critical point. So this has given rise to a contradiction. So the Jacobian of the optimizing function at A acting on B cannot give 0, so it's not a critical point that way through our proof by contradiction. So we've now shown both the if direction and the only if direction, and we've shown that without this Lagrange multiplier. With this Lagrange multiplier, we have a critical point. Without this Lagrange multiplier, we never have a critical point, and that's the entirety of proof 11.2. Again, if you have any questions, please let me know. Send me an email, and good luck on the final exam.